Let me also start recording. Okay, welcome everyone. Welcome to Harvard CMSA Quantum Matter Math and Physics Seminar Series. Let me also So we are very honored to invite Avner Karasik to speak on the Happy New Year Day, Rosh Hashanah, for the New Year. It's a very special occasion. I'm really grateful he agreed to speak on this date. And he will be speaking about his recent work on candidates for non-supersymmetric dualities. Let me remind the audience, please feel free to ask questions and interact with Avner during the talk. And you have 90 minutes, and it's all yours. Welcome. Avner, please take over. Thank you.
Thank you very much, John, for the invitation. And as you already said, for those of you who don't know, today's the Jewish New Year, so just Happy New Year, everyone, Shana Tova. I will talk about this recent paper with Kan Onder and David Tong. It's called Candidates for Non-Supersymmetric Dualities. And in this work, we will explore the possibilities of having non-supersymmetric dualities, in particular in four-dimensional non-abelian gauge theories, and also discuss the obstructions of having such dualities in several cases, and using all the tools that we have to study strongly interacting quantum field theories. And so I will review these different tools, and I will also review and make some comments on familiar examples, familiar candidates for such dualities, and propose new dualities. So, yeah. First of all, just to make it clear what exactly I mean by duality. Duality can have different meanings in different contexts, and also when we talk about the same duality between two theories, it can have different physical interpretation depending on the range of parameters, in particular if one of the theories is asymptotically free and the other can be asymptotically free or IR free and so on. So I will always talk about the case where we have theory A, which is asymptotically free, theory B, infrared free, and duality in this case basically means RG flow from A to B. So when can we have such a scenario of having a low energy physics without symmetry breaking? This will basically, in some sense, will be the question. And I will review the different tools that we have, the non-SUSY arsenal. And all of these things are familiar, but at least for these two, we'll make some new, I think, clarify some subtle points and make some, maybe leads to some new understanding about them. And we'll, as I said, I will also discuss several candidates for non-SUSY dualities, old examples, old proposal made by Adi Harmony and also by Barzani and Cleavage, and make some new comments about them, and a new proposal that we have in the paper, which we call the Barzani-Cleavage plus adjoint, which is basically the formation of this one by adding some adjoint fermion, which this small modification of the theory changes the anomalies and the symmetries in a strong way that we have to change also the proposal for the infrared physics in a non-small way. So we'll start by, many of the things that I will say today are not new. They are known for decades even. So I will start by observing the differences between two classes of 4D gauge theories. So one of them is vector-like gauge theories. In vector-like theories, we always basically have the same IR physics. And vector-like, by vector-like, I mean just a gauge theory where we can write a gauge invariant mass term for all the fermions. And in this theory, unless the number of flavors is too large, and then the theory will not be confining. But typically, what we will always observe in the IR will be chiral symmetry breaking. The symmetry will break into an anomaly-free subgroup. All the anomalies will be matched by the nonlinear sigma model. And always the condensate will be just some fermion bilinear, which is basically the mass term that you can write. And no massless fermions in the IR. On the other hand, in supersymmetric theories, we have a wide range of phenomena. So we can have chiral symmetry breaking also as before, but we can also have many other things. We can have S confinement, we can have a flow to some dual magnetic gauge theory. So we can have a much more interesting infrared physics where the anomalies, for example, are matched not necessarily by Goldstone bosons as we have here, but also by fermions, and also sometimes there will be free fermions, gauge invariant fermions, and sometimes we'll have some other weakly interacting gauge theory. And all these things don't happen in vector-like theories. So first of all, why? Are all these phenomena are special, and are they related to SUSY in some way? Why don't we see them in vector-like theories? So the answer to this question is basically known for many years, and it is due to inequalities that are based on the fact that for all the vector-like theories, the fermion determinant of the Dirac operator is positive. So I will review this version by Weingarten, but there's also, of course, related work by Waffer and Witten, and the same results can be derived using also their inequalities. So let's say we have some vector-like theory, and we can derive rigorous inequalities satisfied at large distances, and we don't need to assume anything about the infrared physics. We don't need to assume a confinement, or we don't need to talk about anomalies or symmetries or anything. So how does it work? Let's consider two very schematic gauge invariant operators. One of them I will call B. B is a fermion. It is a composite operator made out of three fermions, three UV fermions, and this is some gauge singlet combination of them. And the second operator is pi. Pi is a scalar, and it is just composite of two fermions. In QCD, of course, B will be a baryon and pi will be the pion, but this is much more general. So just using the fact that the fermion determinant is positive, we can show that the following inequality is satisfied at large distances. So the two-point function of B is bounded by some constant C, which doesn't depend on the distance, times the two-point function of pi. And it is important that the fermions that appear here are the same fermions that appear here, psi1 and psi2. On the other hand, we know that this two-point function at large distances is just e to the minus mb, the mass of this baryon, this operator, times the distance, and similarly, the two-point function of pi is just e to the minus m pi times the distance. And using this inequality, we know that the mass of B is larger than the mass of pi. So originally, this inequality was used to prove that the proton is heavier than the pion in QCD, which is, well, it sounds quite obvious, but this was done without assuming anything, without assuming confinement, without knowing anything about the infrared physics. We have strong interactions, many things can happen, but still, this is like a rigorous result. The proton must be heavier than the pion. And more generally, we know that this composite fermion in any other theory that we want to discuss must be heavier than a composite scalar made out of the same fermions. So let's say that we have some theory and we want to propose that in the IR it flows to some phase with massless fermions, and the anomalies of the theory will be matched by some massless fermions. Now, using these inequalities, we can show that if we have massless fermions, we necessarily have also massless scalars. And if we have massless scalars in just some gauge theory without SUSY, massless scalars imply broken symmetry. We don't have massless scalars unless the symmetry is broken. So if we have massless fermions, also the symmetry is broken, and the anomalies are all, in some sense, we don't need the massless fermions. So we cannot find in these theories, it's impossible to find an infrared physics without symmetry breaking, actually. So the conclusion is, in vector-like theories, confinement must always come with symmetry breaking, and anomalies cannot be matched by fermions. So all these nice things that we saw that happens in supersymmetric theories cannot happen in these vector-like theories.
Question, excuse me. So the last statement about the vector-like theory confinement must come with symmetry breaking, the symmetry here, is that the symmetry has mixed anomaly with the vector symmetry that is broken? So the vector symmetry, I suppose, is not spontaneous broken by Alpha-Witten theorem, right? So symmetry should be something else.
So the broken symmetry is the anomalous.
Right. Anomalous that has mixed anomaly with maybe the which symmetry
itself. So for example, in QCD, the chiral, the SUNF left at times SUNF right is broken to the vector symmetry. And yeah, it doesn't mean that all the symmetry must be broken.
Yeah, but I just want to clarify, the symmetry breaking is that symmetry that has mixed anomaly with the vector symmetry. The vector symmetry is preserved, right? Oh no.
So okay, let me maybe say it in different way. Let's say, okay, we have anomalies in the theory, and these anomalies can be matched or by a Goldstone boson in symmetry breaking or by massless fermions, for example. These are the two possibilities. Now, if we want to propose that the anomaly is matched by massless fermions, then we can prove that we also have Goldstone bosons, that the same symmetry that we want to match by massless fermions and assume that it is not broken, this symmetry is actually broken because these are the same. This B is charged under some symmetries. It carries some flavor indices due to psi1, psi2, and psi3. And pi carries the same flavor indices of psi1 and psi2. So whatever symmetry that we want to not break in the IR, and we want fermions to match the anomalies for it, this symmetry is actually broken. So it's impossible to match the anomalies by fermions without breaking it. If there is an anomaly-free symmetry subgroup, then we don't need to break it and we don't need fermions, this is fine. So the vector part of the symmetry, we don't need to break it and we don't need fermions to be charged under it. Yeah, does it make sense? Or?
Yes. Let me ask something. So the anomaly here, I suppose you're talking about the whole anomaly of global symmetry, right?
Yes.
These anomalies, I suppose maybe you only focus on the perturbed local anomaly. Is that right? You only consider perturbed local anomaly, or
no? In general,
because in some case for global non-perturbed global anomaly, the IR physics may be matched by some symmetry preserving TQFT or symmetry preserving CFT. They could even preserve a large set of global symmetry without symmetry breaking, even though the theory might have a total anomaly.
You mean,
I mean, for
if I have only discrete anomaly?
Yeah, the global anomaly that classified by Z finite group Zn.
Mm-hmm.
You can match by possibly with certain constraint, but there is many scenarios that you can match non-perturbed global anomaly by symmetry preserving QFT or symmetry preserving CFT. So perhaps you are probably just saying that for vector X theory with some perturbedly local anomalies, and in order to match the anomaly, those scenarios are ruled out. So then, in order to match the anomaly, even with some massless modes, somehow you say some of the symmetry must be broken.
So if we have only discrete anomalies, non-perturbative anomalies, then I think in principle you cannot rule out a phase without symmetry breaking and having a TQFT. I think this will be consistent, and you cannot show, because you don't have a massless fermion or a massless particle that you can use in this type of inequality to rule this phase out. So okay. Yeah, I agree. If you have only non-perturbative anomalies, then maybe a phase without symmetry breaking will be consistent.
And there is also a scenario with the global non-perturbative global anomaly matched by symmetry preserving CFT. That's also massless in some sense. So does that the argument also does not apply?
You mean like a conformal, strongly interacting conformal field theory, or like a conformal window?
Yes, in that case, you can also match some global anomaly without symmetry breaking.
Yes, so this is, yeah, so this inequality and this statement actually said confinement really means we're not in the conformal window here. We can be also in a Banks-Zaks fixed point or in something like this, and it will be fine. It doesn't contradict this inequality. But yeah, but this is like, I will use it soon for specific examples that you can have a concrete proposal. This theory flows to this theory. And everything seems to work, all the anomalies, A theorem, whatever, but still this inequalities tells you that actually this phase is inconsistent. But there can be other scenarios, more complicated ones.
What would be the definition of your confinement here?
So confinement is not really well defined here, but really, I mean, we're not in the conformal window or in some Banks-Zaks fixed point or something like this, as you mentioned.
Okay.
Okay, thank you.
Thanks.
Okay, so as Jovan asked, we can have also other scenarios. So maybe without symmetry breaking, but it won't be. But when we will come to some concrete proposals for such an RG flow, in many cases we will find this type of inequalities rule out the concrete proposals that we have. And in SUSY theories, we don't have these obstructions at all. In SUSY theories, well, first of all, the fermion determinant has this scalar in it because of the Yukawa interaction. So, and this is, we integrate over phi. It can get, takes any value. So this is not positive anymore. Also, we can have gauge invariant fermions of the form phi psi, for example, schematically. And for these type of fermions, we cannot use such inequalities. And also, massless scalars in SUSY theories don't imply a broken symmetry, of course. They're just part of the multiplets. So from all these reasons, the inequalities don't apply. And in supersymmetric theories, we can have there's no problem having massless fermions in the infrared without breaking any symmetry. And therefore, all these proposals as confinement, cyberg dualities, and so on are consistent, of course. So where to look for non-supersymmetric dualities and where not to look for them? So we already know where not to look for them. So for example, maybe the most obvious thing that we can try and do is take some known SUSY duality and just delete all the scalars from the two sides of the duality. Obviously, all the anomalies will still be met because all the anomalies just come from the fermions. And this approach automatically doesn't work. It cannot work for all the vector-like theories, including all the SPN and SON gauge theories, and also the original SUN Seiberg duality, because all the matter, all the fermionic matter is in vector-like representations there. So, for example, let's take some SON supersymmetric duality and delete all the scalars. So we were left with some SON gauge theory with enough fundamental fermions and an adjoint fermion lambda. And we want to say maybe it flows to this theory. Again, the supersymmetric magnetic dual without the scalars. So some SON, SO gauge theory with a different rank. Again, NF fundamental fermions and adjoint lambda, and also some singlet, which we write as psi lambda psi. But now this theory is a vector-like, all the inequalities applies, and from using these inequalities, we can show that if this M is massless, also psi is massless, which is some scalar, and it comes from a condensation of psi and symmetry breaking. So psi will be a Goldstone boson for some symmetry breaking. So therefore, this phase, this infrared phase is not consistent without symmetry breaking because of this singlet that we need to put in the IR. So there are other places where we can look for such non-supersymmetric dualities. So one place is chiral gauge theories, obviously. For chiral gauge theories, the fermion determinant is not positive. And the second is vector-like theories with scalars, but not in a supersymmetric way. So we will discuss these two possibilities.
Sorry, actually, question, go back to what we just discussed. So when you say in the confinement, the MUNS-conf was the symmetry breaking, how is the situation for a smooth confinement or S confinement? What's the comment for that?
So in in supersymmetric theories, you don't have this problem. Because for supersymmetric theories, the inequalities don't apply for all these reasons that I mentioned here. So it is fine. In chiral gauge theories, you also don't have these problems without SUSY, because also the fermion determinant is not positive. And do you have an example of a vector-like theory with the proposal for S confinement? I think that there's no such.
So SUSY's theory fails which condition so that the conclusion does not hold?
For SUSY theories? Sorry?
Yes, for SUSY theory, which condition? Sorry, yes.
So also, first of all, we have scalars in due to the Yukawa interactions, the fermion determinant is already not positive. Second, we can write composite gauge invariant fermions using just two operators, two fields and not three. And basically all the inequalities come from kind of Cauchy-Schwarz like inequalities, applying them in a row. And it is based on the fact that here we have, in some sense, simplifying it, here we have more fields than here. Here we have three, and here we have only two. And this is, at the end, the result why B is heavier than pi. But if you can write a fermion using only two fields, then we cannot, the inequalities just won't work. We cannot do it. And also massless scalars don't imply symmetry breaking in supersymmetric theories.
Okay, fine.
So in all the examples of supersymmetric or chiral gauge theories, S confinement is consistent and the inequalities, we just don't have them.
Thanks.
Thank you. Okay, any other questions? Okay, so as I said, we have, before moving on to examples, we have all different tools for to analyze strongly interacting gauge theories, and maybe the most important one is, of course, anomalies, which is known for decades now. But in the last couple of years, all the story of discrete anomalies received a lot of new attention. I think mainly due to developments in the context of higher form symmetries and how to couple them to background gauge fields. And people studied all these discrete anomalies a lot, and they give new non-trivial constraints on the flow of strongly interacting theories and new consistency checks for dualities. So obviously, if we have new consistency checks, we must use them. Now, if you read our paper, maybe you might notice that we didn't check discrete anomalies at all in the examples, the proposal that we give. And well, you may wonder, okay, why? Something so obvious to do, why didn't we do it, or are we that lazy? So we give the argument in the paper, but I will also review it here. And the answer is that actually, in many cases, I will make it more precise soon, discrete anomalies are completely redundant. They don't give you any new information that's not contained already in the continuous anomalies, and you can just ignore them. So this statement, it might be trivial for some of you, maybe, I don't know, but I think that there's a lot of confusion in the literature about it. So I will make the statement about when we can just ignore discrete anomalies. So let's say that we have two theories, T1, T2, and we want to study, we want to ask if their anomalies match or not. So this is equivalent to just defining a new theory T, which is a T1 plus the conjugate of T2. And then anomaly matching between T1 and T2 is equivalent to no anomalies at all for T. This is just, it will be easier to talk about one theory and ask if it has anomalies or not, instead of talking about two different theories. So now, so let's say that we have this theory T with some symmetry group of the form G, which is H mod gamma. So H, typically it will be something like a product of SUNFs and the U1s just acting on the field. Just we look at the fields in the Lagrangian and we write how they transform. This is the simplest thing that we can write. And later we notice that, okay, there are some central elements inside H that acts trivially on all the gauge invariant operators in our theory. So we need to divide by them. They're not part of the symmetry group. The symmetry group is smaller. So we quotient by this gamma, which can be something like Z and F times something, blah, 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 blah. Depends on the case.
Avner?
Yes.
What do you exactly mean by T1 plus T2 dagger? How do you identify the symmetries of the two theories? Do you couple them?
You don't need to couple them. You just, you have, for anomaly matching, you identify the symmetry in T1 and T2, and you identify the quantum numbers of all the fields for the anomaly matching. So take all the fields in T2, just with the conjugate quantum numbers. Whatever you need to identify, you don't need to couple them. They can be decoupled.
You mean you look on a subgroup, so naively, if you don't couple them, the symmetry is just, the symmetry of the two theories. So you are looking on a subgroup of the global symmetry of this theory? That's what you're saying?
Well, let's say that I couple, let's say I coupled my symmetry group to background gauge fields to analyze anomalies. Typically, that's what we'll do. Then
so couple them to the same field.
In the same way, whatever. So just as an well.
Okay.
In theory 1, I have some SUNF symmetry group. In theory 2, I have some SUNF symmetry group. I identify the quantum numbers of the fields. and then I take T1 plus T2 dagger, they're not non-interacting, but there's only one SUNF symmetry group that I'm referring to.
I agree. You couple them to the same background fields.
To the same background fields, yes.
Okay, thank you.
The full symmetry is bigger, but I'm not interested in it. Yes, thank you.
By the way, just comment about the discrete anomalies, this terminology. Shouldn't it be better just separate the class of anomalies by two cases? One is perturbative local anomalies classified by integer Z class versus non-perturbative global anomaly classified by finite group Cn or torsion, the finite group, abelian group. So when you say discrete quotient anomaly or discrete anomalies, do you try to emphasize something else that I didn't mention?
So these discrete anomalies, if they exist, yeah, they are finite yes. Order necessarily.
For example, the integer Z class perturbative local anomaly also discrete, right? Z is also discrete.
Yeah, I mean finite order, non-perturbative. Yeah, that's right. What I mean by discrete.
So wonder say whether we should just use local and global anomalies because both are discrete in some way. But I think the discrete, maybe you are trying to emphasize the local case. Local anomaly is captured by small infinitesimal deformations of a gauge or diffeomorphism transformation away from identity, then captured by Feynman graph. But the global one is not captured by small deformations, but the large gauge of diffeomorphism transformation.
Yeah, I think it's just a matter of terminology. So I use continuous and discrete. For continuous is a transformation close to the identity, and discrete is some finite transformation. And the same way that continuous will be perturbative and discrete will be replace it by a non-perturbative or global, if you want. Yeah, just a matter of terminology, but I think we mean the same thing here.
And why do you emphasize quotient here?
Yeah, so specifically the discrete anomalies that I will talk about here are discrete anomalies that arise due to the quotient by gamma.
Right, but there are also cases not due to quotient, but maybe include some discrete space-time or charge conjugation, time reversal, symmetry, parity symmetry, that type of anomaly. But they will not be discussed for the case of the global anomaly.
So all these anomalies exist, and if they exist in our theory, we need to study them. I only have new things to say about these specific type of anomalies.
No problem. Okay.
So, but of course, all these anomalies, we need to study them. In particular, a special case of discrete anomalies or global anomalies will be these anomalies that arise due to the quotient by gamma, and studying the faithful symmetry group instead of just the naive symmetry group H. So I want to study H mod gamma.
Okay, thanks. Thank you.
Yeah, thank you for the comments. So we have a symmetry group H mod gamma, and let's say that H is anomaly free. And in H, so we matched all the perturbative anomalies of H, if you want. And do we need to worry about anomalies in G? So when we take this quotient by gamma, can we get new anomalies that we didn't have when we only considered H? So the answer, the statement is that if H is anomaly free and pi 0 of H is 0, then also G is anomaly free. Automatically, we don't need to worry about new anomalies that arise due to the quotient. So why is this true? When we assume that H is anomaly free, it means that if we couple H to some background gauge fields, FH, under a variation of the action by some element in H, the action changes by something that looks like this, where K is some integer, and the trace of f with F is quantized in this way. So in total, the partition function is invariant under this transformation. This is what we mean by when we say that H is anomaly free. Now, if pi 0 of H is 0, it means that all the elements in H are connected continuously to the identity. For the identity element, obviously K is 0, because this is just the identity. And therefore, for all elements in H, K is just 0. So if pi 0 of H is 0, then delta S is identically 0, not just 0 mod 2 pi. It is just 0. Now, instead of just coupling H to background gauge fields, let's couple H mod gamma to background gauge fields. Nothing changes. We still have delta S equals 0. The quotient by gamma doesn't do anything. So H mod gamma is anomaly free. So if H is anomaly free and pi 0 of H is trivial, then also G is anomaly free, and we don't need to worry about these discrete quotient anomalies in this case. If pi 0 of H is not 0, then the non-trivial elements of pi 0 of H are not connected to the identity, and they can have K, which is non-trivial. If we have such elements, then once we take the quotient by gamma, the thing that the quotient by gamma can do is lead to a fractional quantization of trace F wedge F. Now, this will not be integer anymore, but it can be some 1 over n, for example. And now when we take the quotient by gamma, we get new anomalies. We find that delta S is not 0 mod 2 pi, but it can be shifted by some fractional number. But this can happen only if pi 0 of H is non-trivial. Only then the quotient by gamma can give new non-trivial anomaly matching conditions. If not, then all these anomalies are completely redundant and we can just ignore them. And just I will go over a familiar example first, just to see an application to this statement. So the example will be massive QCD, just SUN gauge theory with NF fermions in the fundamental representations, and the same mass for all of them. So the symmetry group acting on the fields, on the fermions, is H mod gamma, where H is just SUNF vector times U1 vector, and gamma, the quotient will be ZNC times ZNF. When we study the faithful symmetry acting on gauge invariant operator, we need to take this quotient. Now, H is anomaly free, just a vector-like symmetry. Pi 0 of H is 0. Therefore, also H mod gamma is anomaly free. We don't get any new anomalies when we take this quotient. Another thing that we can do is to include inside our symmetry group also, for example, the shift symmetry of theta by 2 pi using this idea of anomalies in the space of coupling constant. So we don't take only the transformation of the fields, also the transformation of the parameters. And theta goes to theta plus 2 pi is the symmetry of the theory. And this gives us another factor of z in H, in the numerator. So H is now SUNF times Z1 times Z, where Z acts on as theta goes to theta plus 2 pi. The quotient is the same as before. H is still anomaly free, but now pi 0 of H is non-trivial because of this Z factor. So in the second case, when we include also this Z, we can have new anomalies that arise when we take the quotient. So we can have anomalies between the quotient by gamma, between gamma and the non-trivial elements of pi 0 of H. So we can have anomalies between this quotient and this shift symmetry of theta. And indeed, this is what happens when the greatest common divisor of NC and F is larger than 1, then we have such an anomaly between the quotient and transformation of theta. Good. So I'll just make another comment about this. No, actually, I will skip this one. Maybe I'll go back to it later. Okay, so now after this comment, if there are no questions, let me go over some examples. So the first example is due to Adiermoni. It's inspired by a non-supersymmetric duality. So as we already said, if we just take, for example, an SON duality, supersymmetric duality, and erase the scalars, inequalities rule out a chance of having a duality. Now, instead, we can try and do something else. We can start from the SON supersymmetric duality, which is written here, SON gauge theory with NF fundamental multiplets, adjoint lambda, which is part of the gauge multiplet, of course. And within some range of parameters and C and NF, it flows to SONF minus NC plus 4 gauge theory with NF fundamental multiplets. Lambda is again part of the gauge multiplet, and a singlet multiplet, which we write here like this. So if we want to modify it in some way, we must keep the scalars, but one thing that we can do is to change the representation of lambda. Very small modification in the UV. Instead of adjoint in SON is of course a 2-index antisymmetric representation. We can take it to be just the 2-index symmetric representation. And then to fix the anomalies, we will need to do some small modifications in the IR. So again, also this lambda, we take it to be in the symmetric, and we need to change the rank here. Instead of +4, we have -4. All the anomalies work. So this is like a new proposal for a non-supersymmetric duality. We can justify it in using some arguments. So in the large n limit, at least, the adjoint and the symmetric behaves the same. So the scalar phi that we have here are expected to remain massless for a long time, because the mass in the large n limit, the mass will be suppressed for the scalar. And if the mass of the scalar is much smaller than the strong coupling scale, where the scale where the duality takes place, then the scalar save us from the inequalities. So this phase is consistent. The dynamics of the theory is almost supersymmetric. In the large, it's up to 1/n corrections. The dynamics will be supersymmetric. So we expect that this dynamics will be similar to the supersymmetric ones, and we expect that this duality will hold. The only problem or feature of this proposal is that to get this behavior, we need to fine-tune the many parameters in the theory. So when we have scalars, we have Yukawa couplings, we have scalar potential, and all this story can happen only if we fine-tuned the scalars to the regime which is close to the supersymmetric one. It is close to the supersymmetric one, but it is not really close to the supersymmetric one in the sense that there's no new symmetry if we take the Yukawa coupling and the scalar potential to be as in the supersymmetric case. So it is really fine-tuning. It's not we don't have an emergent symmetry at this point. So we expect that only when we fine-tune the parameters in some way, we get this duality away from this fine-tuning line or whatever. The mass of the scalar will get a mass, which is typically will be larger than the strong coupling scale. If it is positive, then we integrate the scalar out at some higher scale. And then due to the inequalities, this duality is not consistent. So we get something else here. And if the mass is negative, the scalar will break the symmetry and fix the gauge group. So also here we will get something else. So unlike this, in this fine-tuned regime, we can get this type of duality. Now, a second example, which is also very familiar.
Can you go back, please?
Yeah.
So in this case, you have a theory which flows to something else in the two phases with m squared positive and negative?
Yes.
And how do you know that there is no first order phase transition between these two phases?
Well, really, I don't know anything. But
So in what sense do you know that the theory at the bottom is really there in this red region?
So at least in the large N limit, first of all, in the large N limit, and if we fine tune all the parameters in the UV to be similar to the supersymmetric ones, then the mass of the scalar will be suppressed in the large N limit. And then we can expect this, which I don't know anything for sure, but I can expect that the dynamics will be similar to the supersymmetric one, because in the large N limit, this is almost the same theory as the supersymmetric theory.
Is there, in the supersymmetric theory, is there a potential for phi or not?
There's only a, no, there's only a Yukawa coupling.
Okay, and certainly there are flat directions for phi.
So you're asking if there's a runaway or something,
for example.
so
I want to know one place where you have an argument that this duality is valid. So for finite n, I see no argument that the tuning would help. There would be a phase transition. It might be a first order transition.
yes.
So now you've changed the problem. You said large n. And you said that for large n, we can basically think about the supersymmetric theory with a small deformation.
Yes.
But then the sign of the mass square on one side could be positive and negative on the other side. It could be flat direction there, so we don't know what's going on.
So if whatever happens to the scalar happens way below the strong coupling scale, you can say that they will not, you can ignore their mass until after the duality happens.
But
you mean the scalar that should be here? Yes. Yeah. Okay. I think I see. So if it was a supersymmetric duality, there were scalar also in the IR, and these scalars can become massive, or their mass can be negative. So in this infrared theory, we can compute the one loop correction to the mass of the scalars that should be here, and see if it is negative or positive. Is that what you're asking?
well, I thought that people calculated such things, and typically it's negative.
So actually, it depends on. So there are two theory. I mentioned only the SON, but there's also the SPN. And for one of them, it will be negative. One of them, it will be positive. The reason is that just the one loop, you can compute it. And basically, the reason is that for one of them, you change the fermions from antisymmetric to symmetric, and in the other from symmetric to antisymmetric. So in one of them, you increase the number of fermions. In one of them, you decrease them. And the fight between the bosons and the fermions that want to give positive or negative mass to the scalar. In one case, the mass, if we take the SON versus the SPN, in one case, the mass will be negative. In one case, the mass will be positive. So in the case where the mass is positive, you can say that you get the scalars here and they just become gapped, and you can ignore them and you get this phase in the IR.
Okay, thank you.
So this is something that you can compute. Harmonic did it in his paper about it. Yeah, and in the other case, you can also say that, okay, this duality works. We get a scalar, and then at this point, the scalar their mass becomes negative, and we get some symmetry breaking from here, from this point, which is, it's a different story. We still get symmetry breaking at the end, but we in some sense, we also know what's going on. And it is some non-trivial dynamics. Okay, so now there's also a famous story known as the Barzi and Cleavage theories. So here, basically, we start from in the UV from an SUN gauge theory with some fermion in symmetric representation, Q fermions in the anti-fundamentals, and P fermions in the fundamental representation. And to cancel gauge anomalies, we need to have this relation between Q, P, and N. We have this symmetry group SUQ acting on psi, SUP acting on psi tilde, and two U1 factors, which are non-anomalous. And it was conjectured by Barzi and Cleavage that this theory flows in the IR to just three gauge invariant composite fermions that we can write like this. And all the perturbative anomalies match. So there are two different problems in the literature with this proposal. So two claims that this phase is inconsistent. One in the large N finite P limit, and two, it is inconsistent for any value of N and P due to some new discrete quotient anomalies. So I will go back to this large N finite P story later at the end. It's quite technical, but the discrete quotient anomalies is very simple. And the answer that there are no discrete quotient anomalies in this theory from the reason that I explained before. So H is just SEQ times SUP times U1 times U1. Pi 0 of H is 0, and that's it. Basically, there are a lot of arguments in the literature why showing that there are some subtle anomalies when you couple this theory to the background gauge field for the quotient, but it just doesn't exist. It cannot exist due to this very simple argument. All the perturbative anomalies for H match. There's no doubt about it, and therefore also all the anomalies for G, which is H mod gamma, whatever gamma is, it doesn't matter. I don't need to check what it is. All these anomalies are also matched automatically. Okay, so now there's a small generalization of this theory. We can modify this Barzi and Cleavage theories by adding just a new adjoint fermion lambda in the UV. Now, the symmetry group in H, we have another factor of U1. This theory has 21 independent anomalies. There's no known free fermion phase. This theory hadn't been studied. It hadn't been studied in the literature as far as we know, but we couldn't find any free fermion phase for this theory. And we can ask, can we find a consistent infrared candidate without symmetry breaking? And we can also take some insights from supersymmetry, because when we have an adjoint fermion, one thing that you can try and do is supersymmetrize the theory and see what's happening. So the proposal that we had in the paper is that this theory can flow to some spinite gauge theory with this matter content. We have, again, a fermion in the adjoint representation. We have different fermions in different 8-dimensional representation. So P fermion in the 8S, Q fermions in 8V, and one fermion in the 8C. And in addition, we have 4 singlets. And from the number before tells you how many fermions of this type we need to have. So this tells also the representation. So we have sigma S in the symmetric of SUQ, sigma A in the antisymmetric of SUP, rho B in this bifundamental of SUP times SUQ, and one fermion U. So all the anomalies for this between these theories match, obviously. And now, what is the motivation behind this weird proposal? So, for example, why spin 8? Maybe you can find the SO17 or SU5 or whatever. It looks a little bit random. So where does this 8 come from, for example? So 8 has the special property that it equals 4 minus minus 4. So how is it related? So remember that Q, P, and N are related. Q is N plus P plus 4. Now, when you analyze the symmetry group of the UV theory, you can show that gauge singlets must have 2 or actually even number of SUP times SUQ indices. This is for sure true when P and Q are even. The reason is that when P and Q are even, there's a common Z2, there's a Z2 central element, which acts as the Z2 center of SUP and Z2 center of SUQ. And this element acts trivially on all the gauge invariant operators. So whatever the theory flows to, all the gauge singlets must have an even number of SUP times SEQ indices, because the Z2 must act trivially on them. So fields that are charged under SEQ and SUP must have basically 2 indices. They can be symmetric, anti-symmetric under one of them, or in the bifundamental of the 2 of them. And there are no other options. So now we can try to match the anomalies. There are 21 anomalies. I won't do all of them here, but just as an illustration, let's take just one of them, the simplest SEQ cube anomaly, and similar story for the SUP cube. So in the UV, we just have N fermions in the fundamental of SEQ. So the anomaly is N, which is Q minus P minus 4. In the IR, we can have a singlet sector and a gauge sector. So singlet sectors, as we said, the ingredients we can use are symmetric, anti-symmetric, and bifundamental, so they can give us Q plus 4, Q minus 4, and P, contribute to the anomaly. And now we can play with the singlet sector and ask, okay, what is left for the gauge sector? So the simplest thing that we can do is just match everything using the singlet sector. So 0 is left for the gauge sector. And this is exactly what happens in the Bose-Yank Cleavage theory without the adjoint. There we don't have a gauge sector at all, we just have a singlet sector. All the anomalies match using 3 gauge invariant fermions, but this doesn't work here due to the new anomalies that we get when we add this lambda. So the second thing that we can do is to get here -8 remaining for the gauge sector to saturate. So this is basically where this 8 comes from. We need something with 8. We need 8 fermions. We need contribution of 8 to the anomaly. So we need 8 fermions in the, for example, the fundamental of SEQ, and 8 fermions in the fundamental of SUP. And this is something that we can get using this spin 8 theory. And as I said, another thing that we can do is try to complete it to a supersymmetric theory. So for the P equals 0 case.
Maybe let me ask one thing.
Yes.
Are you the duality between the left and right works for any SUN for any N?
No, at the end I will give you like a phase diagram. Obviously, we need to be consistent with the A theorem, and well, it only makes sense when this is asymptotically free and the other side is IR free. So there's some regime. I will show you soon.
Okay.
Oh, for p equals 0, we can we just have this theory. We can add scalars that complete it to a supersymmetric theory, and also the other side in the IR, and then we get actually a known supersymmetric duality due to Pouliot and Strassler, where the quantum numbers of the singlets are fixed by some superpotential that I wrote here. So this is a non-duality. So our proposal is just for p equals 0. It is just what happens when you erase the scalars. In this case, it is fine because the UV theory is chiral, so we don't have the problems that we mentioned before. What happens for higher p? For higher p, actually, there's no SUSY completion, which is a little bit surprising. So we have this field content, the gauge sector and the singlet sector, and to fix the quantum numbers of the singlet sector, we need to add some potential that couples them. So if we try to write some 4 fermion potential, this is what we need to write. So the details are not very important, but one thing that you can see is that we use here S dagger, just the conjugate of S, and this potential cannot come from a holomorphic supersymmetric potential. And you can try and do, okay, well, this is just an example of one way to maybe to fix the quantum numbers of the singlets to be whatever you need to match the anomalies. We can try to write the most general, also maybe very irrelevant potential that fix the quantum numbers for all the fields using some holomorphic potential, whatever it is, and it's just impossible. So this, for p larger than 0, there's no SUSY completion, and this duality is in some sense inherently non-supersymmetric, even though it is in some sense inspired by SUSY for p equals 0. When you add more fields, there's no SUSY completion due to this problem of writing the holomorphic potential. Okay, and then as Juven asked, does it work for any P and Q and N? So N is fixed by when you fix P and Q due to the gauge anomalies. So this is a diagram for the proposed physics of this theory. So in the white regime, Q is smaller than P plus 6, so we don't have, N should be smaller than 2 in this regime. So we just don't have a theory here. Here, the UV theory is IR3. Here, the duality makes sense, is consistent with the A theorem, where here, the spin 8 theory is infrared free. Here, the spin 8 theory is also asymptotically free as the UV. And here, the proposal is not consistent with A theorem. So basically, our proposal makes sense in this orange-yellowy regime. Here we have maybe some kind of conformal window, and here the UV theory is IR3, so we know what it is. So this is the full proposal for this duality. Now the opposite here in the purple, just I'll make a comment, the spin 8 is asymptotically free, and the SUN is IR free, and maybe you want to say that the duality flips side, so the spin 8 flows to the SUN, but this is inconsistent again because of the same inequalities that we talked about. The spin 8 is vector-like, and the inequalities just forbid you from having this duality. Okay. Any questions?
So, sorry, the proposed duality works in the yellow region.
Yes.
And what are the boundary that parameterize the valid region? What bounds the? Maybe these are simple equality. If you can spell out like the boundary of the validity of this duality.
So we have two things that we need. So three actually. We want the UV theory to be asymptotically free. This is true. This is not true only here. Here the UV theory is IR free, so it is. It doesn't flow to anything interesting. We want the duality to be consistent with the A theorem, and this is true in the yellow and red regimes. And we also want the spin A to be infrared free. So we have a flow from some UV asymptotically free theory to a weak link to an infrared free theory in the IR. So here the spinette is also asymptotically free by itself, so it also flows to something unknown, maybe. And here in the green regime, it is not consistent with the A theorem. So only in the yellow regime it is consistent with everything. Okay.
Do you provide just the parameterization of the boundary in terms of P and Q? Maybe there's some just linear equations or something.
The explicit formula you want?
Yes.
Well, I have it we have it in the paper. It is not linear. The A theorem, so the value when it is asymptotically free or not, just the one loop beta function, it is linear in P and Q. And like maybe I can tell you what it is, but A theorem is nonlinear. It is quite ugly and complicated. No, it is very nonlinear equation, the A theorem. It looks linear because in the large N limit, it is more or less in the large N limit, it is more or less N equals 0.31 Q. But it is for small N, it is non-linear. Okay, just a computation of the anomaly for the UV in the IR. Okay.
So thanks.
Okay. So now, well, this was our proposal. I would make a few more comments about large N and some new understanding that we have about it, which are related both to the Bar-Zinkelevich proposal that I mentioned before and to this proposal, which the two of them seems to be inconsistent in the large N limit if you apply some argument due to Eichten-Press due to these people, but actually we think that this argument is not correct, and we want to give a refined argument. And the two proposals, both the original Bar-Zinkelevich and our proposals, are consistent in the large N limit, is what we claim. So before I go to this, are there any questions? So this will be the last part of the talk.
Maybe can you help to say the physical statement what A theorem constraint for the P, Q, and N just by words? Can you say a few words? Because A theorem seems a black box, hide something.
To explain, sorry, yeah,
for certain P, certain Q, for this number of for fermions or whatever, what does A theorem try to constrain?
So yeah, so whenever we have a flow from some UV theory to some IR theory, the flow must be consistent with this A theorem. So the A is some number that you can compute for any theory, and it gets some contributions from all the fields that you have, from the gauge bosons, from the fermions, from the scalars. Each one of them contribute some amount, some number, basically, and you just need to add up all these numbers. If you have more fields, then A will be bigger. And the statement is that A must decrease under the RG flow. So a flow from theory A to B is consistent only if A of the UV is bigger than A of the IR, which it is also maybe more famous is the C theorem in 2 dimensions, which is a similar number that you compute for the UV in the IR, and the flow must be and it must decrease under the RG flow, which is intuitively it is the statement that the number of degrees of freedom decrease as you flow to large distances, low energies, because you integrate out degrees of freedom. So in some sense, you have less fields.
So what's the equality you write down? So I suppose you compute this from the UV and compute from the IR. And
yes,
you try A at the IR is smaller than A is UV.
yes.
Right?
So in the UV, I have some number of gauge fields and some number of fermions, and every gauge field contribute. I don't remember exactly the numbers, but there's some contribution from every gauge field and some contribution from every fermion, and I can compute just the number of fermions. The number of gauge fields in the UV is n squared minus 1, because I have an SUN gauge group. So the contribution to A will be n squared minus 1 times some number that I don't remember now what it is. And the number of fermions will be, I just count the number of fermions that I have here. This is Q times N, P times N, N squared minus 1, and so on. So just the number of fermions times some number, which is the contribution of one fermion to A. And I do the same thing for the IR. So in the IR, from the contribution from the gauge fields is just 63 or whatever. So it remains finite as I take n to be large. On the other hand, the contribution for the SUN theory becomes larger when I take n to be large. And the gauge fields are really leading in are the most important thing. They contribute the most. So the expectation, and this is indeed what happens, is that when you take n to be large, always the SUN theory will have a bigger A than the spin A theory. It has more fields. It is intuitively the same as having more fields, but this is basically some numbers times the number of gauge fields plus some number times the number of fermions. And similarly for scalars, if you have. So you just need to compare these two numbers. If one is bigger than the other, you have a flow from one direction. And that's it.
But you also mentioned the inverse RG flow does not work. Is that right?
So the inverse RG flow would work, is allowed in this small purple regime, but it is consistent with the A theorem. Now the sign of AUV minus AR is flipped, but it is inconsistent with the Weingarten inequalities. Because we want to start from some spin A theory, we want to flow to a theory with massless fermions, and it will just won't work. Because if we have massless fermions, we must have also massless scalars, and the symmetry must break. So the opposite flow is inconsistent due to the inequalities, but it is consistent with the other things.
Yeah, thanks.
Thank you. So, okay, so I will just, the last part will be this large N argument. I will review the original argument by these people. And then I will give a similar but a different argument for how we can use large N to constrain the low energy physics in a way that still makes our proposal and the original Bar-Zinkelevich proposal consistent for any value of N. So the idea is we want to use large N to constrain the spectrum of massless particles. It can be fermions or bosons. And they had the following statement that, as I said, the free fermion phase of Bar-Zinkelevich is inconsistent for large N finite P. So just the flow of Bar-Zinkelevich to 3 gauge singlet fermions that I mentioned before is inconsistent at large N. And using the same argument, you can also show that our spinate proposal dual is also inconsistent for large N finite P. So what is the argument? I will just go over just to remind you some large N rules quickly. So this is in QCD. In general, just the large N counting tells you that if you have some planar diagram, a diagram with NG gluballs and NM mesons, these are the gauge invariant operators that you can write, ignoring baryons for now. So simple gauge invariant operators that you can write, you might be interested in their correlation function. So you put insertions of gluballs in blue and mesons in green. So a general correlation function, the leading contribution scales with N like this, as written here. If there are no mesons, only gluballs, then the scaling is this. So the operators, the mesons and the gluballs are normalized such that two-point function is of order 1. This is the normalization that we choose, and then all the other correlation functions are fixed from this normalization. And a consequence of this behavior is that in the large N limit, we can compute, for example, the decay of gluballs, and this will come from a sum over all the final states over the diagram, the 3-point function of glubal to 2 gluballs squared plus sum over all the states, all the final states, glubal to 2 mesons squared, and so on. And in the large N limit, it scales like just from counting the number of final states, and from this scaling, it scales like an F squared over N squared. So if an F is small, much smaller than N, then these gluballs will not decay, basically. So for small NF, the mesons are massless. Okay, it is not related to small NF, to large N or small N. The mesons are just massless. The pions, because there are Goldson bosons, the symmetry is broken. Yet nothing decays to them. We have massless non-interacting states. Now, what are the large N constraints that were made by Eichner, Preskill, and these people I mentioned before? So, first of all, theories with fermions with in some 2-index representations like symmetric, antisymmetric, adjoint, basically everything works the same. They behave exactly like gluons from the large N perspective. So chi, the symmetric fermion that we had before, behaves like a gluon in the diagram. All the operators sandwiched between 2 fundamentals, like this fermion psi chi psi, behaves exactly like a meson, and all the operators which are traced over like a glubal behaves like glubal from the large N counting perspective. So the statement was that if an operator is to condense in the n goes to infinity limit, we demand that the state with the quantum numbers of that operator appears in the cut planar diagrams. This requirement, along with confinement, greatly restricts the possible realizations of the flavor symmetry. And later, for this balancing cleavage theory, in the large n limit with n is what we called P, held fixed, this realization of the symmetry is not possible because and the fermion, this composite fermion, do not appear in the leading cut diagram. So their claim was that if we want to have a massless particle in the IR, for example, we want to say that this fermion is massless, it must appear in the cut of leading planar diagrams, which is equivalent to saying that this fermion, that things decay to this fermion. Okay, so to summarize the argument, the composite fermion carries two SUP indices, and P is small, where n is large. So there are small number of components because it scales like P squared. Nothing decays to this fermion, as we said, just large and counting. This is the same thing as saying that this fermion doesn't appear on cuts of planar diagrams. Therefore, the claim was that massless particles should appear on cuts of planar diagrams. Therefore, the claim was that this fermion cannot be massless. If this fermion cannot be massless, then the phase is inconsistent because it was part of the proposal. And using the same argument, one can argue that R sigma A in the spin 8 proposal, which was also had two SUP indices, also cannot be massless. So this was the argument, but actually, we think that this argument, everything is correct until this last statement that massless particle must appear on cuts of planar diagrams. We know that this is not true. For example, pions in QCD are massless and they still don't appear. Still nothing decays to them. They're still non-interacting. There's nothing wrong with having massless particles that don't appear on cuts of planar diagrams. And our conclusion is that this fermion can be massless. So I will just finish with a refined large N argument, which is very similar to their argument, but with sometimes different conclusions. So we want to ask if a fermion can be massless or not. If we have some chiral gauge invariant composite fermion psi L, we want to ask if it can become massive in the large N limit, then we want to be able to write some 3-point function between psi, another fermion, which actually can be also the same fermion, it can be also a different fermion, and some scalar, and we want this scalar to get Vev. Then it gives a mass to the fermion. Now we can, using the large N counting, we can estimate the scaling of this coefficient y, and we can estimate, we can also write a general potential for the scalar phi and estimate the Vev that phi can get if it gets a Vev. And then we can estimate the large N scaling of the mass that psi get. If the mass is small, is suppressed in the large N limit, then the fermion psi remains massless. If the mass is large, is not suppressed, psi can become massive. So applying this to our theories, for the Barzen-Cleavage theory, this scalar operator can be used to gap psi2, psi3, and some of psi1. It also breaks some of the symmetry, but we can conclude that psi1 must remain massless. There's nothing that can give mass in the large N limit to psi1, and it must remain massless. And also these fermions that can be gapped, they can, but they also, the argument only tells us that the fermions can become massive, but nothing tells us that the fermion must become massive. So we think that there's no argument that forbid fermions from being massless due to large n. And okay, the last part was a little bit fast and technical, but I hope if you have any question about it, please ask. I think I will finish here. So just a summary, I mentioned these different possibilities for non-supersymmetric dualities. So we can have fine-tuned dualities, which comes from vector-like theories plus scalars. We need to fine-tune the scalar potential to get these dualities, or generic without fine-tuning if we start from a chiral gauge theory. And okay, we talked about discrete anomalies and large n, and even though there are some arguments forbidding this free fermion phase for the Barzen-Cleavage theory, we actually think that the two arguments are not correct and the phase is consistent. And we gave this new proposal for the duality SUN flows to the spin 8 that can be consistent for some range of parameters. And that's it. Thank you very much. Shana Tova.
Thank you very much. Thank you very much, Toda Rabba. Thanks. Question from the audience, comments, please feel free. Maybe too naive question. Why does spin A plays an important role here? And secondly, what are some additional checks? So maybe the future steps that one should take to take the duality proposal more serious, even more serious.
Yeah. So for the spin 8 will come, as I mentioned, well, two reasons why we thought about the spin 8. So one of them is the fact that for p equals 0, there is a known spin 8 dual in the supersymmetric case. So spin 8 appears in the supersymmetric p equals 0 theory. Whether it does or not appear for higher p, we don't know, but it is consistent. And the second reason is that if you try to match the anomalies, you have two possibilities: to get no gauge sector or contribution of 8 to the anomalies from the gauge sector. And contribution of 8 you can get only from such a spin 8 theory. This is basically the only possibility that we think that can work for any P and Q. And the second was how to give additional checks. I don't know, we need to improve our ways to study strongly interacting gauge theories. Maybe put chiral gauge theories on the lattice, which we don't know how to do, but.
Okay.
Yeah. I wish I had better answers to this, but.
Professor Matt Strassler has a question. Matt, please.
Yeah, one of the key checks, one of the key ways, of course, the supersymmetric cases were checked is that there were all sorts of flows between the different theories. You could check that the flows matched across the duality. Here, there is one that you didn't mention, right? That you could add a mass for the adjoint on the SUN side, and you should recover the Barzen-Cleavage result, but you didn't tell us how that works.
Yes, this is a good question. So, what we think that happens, so if we add a small mass to this lambda in the UV, the thing that will happen in the IR is, the only thing that can happen is that this lambda tilde will get a small mass. This is the only thing that is consistent with anomaly matching. Now, as you increase the mass, So one possibility is that this theory will flow to the free fermion phase of Bar-Cleavage, but this doesn't seem to happen. So there should be, if this scenario is true, for some value of the mass, there should be a phase transition in the UV. So this theory, the IR theory, spinning theory doesn't flow to the free fermion phase of Bar-Cleavage. If it was true, as you said, it was more convincing. But if this is true, you have some phase transition at some large, finite value of the mass.
Okay, well, I think that's clearly an answer to Juven's question, is that if this picture is going to be consistent, one has to also develop a consistent picture of what happens across that transition, if it's possible to do so.
So it is possible, but it doesn't go, the transition doesn't happen in the IR. It happens already in the UV, and you just get flow to different theories. I agree that it would have been more convincing if you had a flow from the spinate to the free fermion phase, but yeah.
Okay, thanks.
Thank you. There was something in the chat.
No, so Justin Kaup is asking, is chiral symmetry breaking not independent of confinement in non-SUSY theories?
Know that you have confinement with chiral symmetry breaking in n equals to 1 gauge theory with NF equals NC, but no chiral symmetry breaking if NF equals NC plus 1. So do you mean independent of confinement in non-SUSY? So I want to know if you can have confinement with non-confinement. Yes. So the answer is in vector. So the claim is in vector-like theories, unless you have some scalars and maybe fine-tune their potential, you will always have chiral symmetry breaking. You will always have a symmetry breaking to an anomaly-free subgroup. But in chiral gauge theories, you can have confinement without symmetry breaking, and the example is this example. So in this theory, you start from a non-SUSY chiral gauge theory, and the proposal is that you flow to some kind of S-confining phase. You have here, you just have free fermions, so you have confinement without symmetry breaking. Does that answer your question? Oh, good, thank you. Obviously, we don't know if it is true or not, because studying chiral gauge theories is very hard. It's the hardest thing, the hardest type of theories to study, because we also cannot study them on the lattice. But this is just a proposal. We believe that this phase is possible, so that you can have a confinement without chiral symmetry breaking.
Oh, is there one more question? Let's see. Let's see.
I just wanted to follow up if nobody else has another question.
Please.
So can you go back to the picture with the SO8 theories on it, so I don't get confused about what the theory is?
This one?
Yeah. So is it so there's some regime where the theory on the right is infrared free, but when you add a mass for the adjoint, the resulting theory is no longer infrared free, presumably.
Mm-hmm.
So can you have a proposal in that regime where the resulting spin 8 theory confines? And in that case, can you ever get the physics of the, just sort of, looking at sort of consistent, the states that you have that you could potentially confine
No,
Can
I
you-
think that you cannot. Unfortunately, I think that you cannot, because even if once I give mass, so if I know what happens if I add small mass here in the UV, I add small mass to lambda tilde in the IR.
Yeah.
And then let's say it's at low energies, I can ignore it, I integrate it out. Now, this theory, this spinate with this fermionic content, something will happen to it. I don't know what. But the things that, the point is that the things that couple, that give you all the symmetry structure, all the anomalies that you want them, that will be consistent with the free fermion phase, are only when you fix the quantum numbers of the singlets to be something specific. But the dynamics of this spinate theory will not depend, will be completely independent of the singlet sector, because they couple only through irrelevant operators. So I think that you won't get a free
They
fermion.
might be relevant operators, but the couplings aren't zero. I mean, that's kind of the question here, right? I mean, you may need those irrelevant operators to remove various states, make sure they're massive, and then check to see which ones are left over. That would be the question.
Yes. So I think, okay, we didn't do this analysis very carefully, but I think that you can get, so for example, if this spinate confines after you integrate out the lambda tilde, you can get some states in representation of SUQ and SUP, and some of them will get a mass term from the irrelevant terms, and will be gapped together with sigma S, sigma A, and all these people, and you will remain only with the Barzen-Cleavage free fermions. So because it's always the opposite. So here, for example, sigma S is in the symmetric representation.
Mm-hmm.
In the free fermion phase, you need the antisymmetric. So this symmetric can gap a symmetric part from something that you get from this confinement, and you will have only the antisymmetric in the deep IR, which is what you need for the free fermion phase. This is something that I think can happen, and we said that maybe we'll do it, but at the end we didn't do this analysis. And thank you for reminding me.
I would be very interested to see if it can be made to work. It wouldn't surprise me if it can, because the anomalies have to match somehow. But
Yes.
also, these irrelevant operators they have to be important. Otherwise, you have too many symmetries.
Yeah, that's what I said. So if they're becoming important in the IR and give you a mass term, you maybe you can get it. I need to check.
Thanks.
Thank you for the question.
Okay, thank you. Any further question, comments? Right. If not, we shall thank Avner again for the wonderful seminar. Thank you very much.